For some reason, maybe not in the full screen mode, yes, or?
Now we see not in full screen mode.
But anyway, I will start. Maybe it's not so important.
Yeah, okay. But if you can change here, you have to try to
okay.
show full screen mode.
Yes, okay. Just a moment. Is it working now?
Yeah,
okay.
We see full screen.
So situation which I would like to say about is we are interested in ratio when we have ratio of two intensities. One is intensity of plasmon coupled emission. It means that near the emitter, it can be some fluorophore or it can be some scattering center which gives some Raman scattering. We have metal nanoparticle, and this system make interaction, and we have in the numerator this plasmon coupled emission intensity, and in the denominator we have intensity from emitter which shines without the nanoparticle. When I say about plasmon, what I mean that when we have a frequency of incident light, and this frequency become very close to the plasma frequency of free electrons, free surface electrons in the metal nanoparticle, and this relation can be written also in terms of permittivities, which I like more. When we have permittivity of metal, in case of resonance, it should be twice higher than permittivity of dielectric environment, and it should be negative. And why I like more this second ratio in terms of permittivities, because it allows us to make very quick judgment about wavelengths of plasmon for nanoparticle consisting of any metal. Basically, we can go, for example, for refractive index database, and in case of gold, we can just estimate. These data are tabulated in the internet, so you can just take an epsilon from environment, make it twice, by modulo twice higher and negative, and see at which wavelengths you will see the resonance. And you see that for gold particles, for example, in water, it will be in the range of greenish light. It means that in this greenish light we will have a strong absorption, but in transmittance we will have transmitted red part of light. And indeed, these colloids of gold nanoparticles have red color. And here you see the photograph of colloid which was made by famous English scientist Michael Faraday. He was fascinating about this ruby colors of these solutions, and he prepared a lot of them, and they were quite stable. And this kind of bottles stayed from the Faraday time to the Second World War time without sedimentation. So, and the same effects also are present in even in more ancient samples. For example, here you see this Lycurgus cup, which came from ancient Roma, and it appears that this ceramics contains also some small gold particles, which also provides the same effect. It's red in transmittance, and in reflected light it has greenish tint. And this seen in scattering or in reflection mode, it's even more interesting because it allows to visualize nanoparticles. So usually when we say about nanoparticles, they have sizes less than the wavelengths of light, and in common geometry of microscope, it's impossible to see them. But if you make a dark field, means that the direct light will not come to the particles, but only some side scattered, you made side excitation and only some scattered light comes to your eye, you will see that this bright spot, basically it's a scattering from nanoparticles. And it is visible because the cross-section of scattering is kind of in times higher than the geometrical cross-section of particle. And by such trick, you can visualize the particles, and even you will see the different colors, and by color you can judge about the shape of particle if you have some experience. And further interesting example is so-called surface enhanced Raman scattering. It's a scheme when you excite with some frequency your sample, but scattered light, very little part of scattered light has some frequencies which differs from its excited frequencies. And usually this effect is very small, but it was recognized in 1974. This guy, Professor Martin Fleischmann, he recognized that it's possible to obtain several orders enhancement from the Raman effect when you deposit the analyte on the top of a nano particle surface. And initially it was quite funny that initially people did not believe him much, because he also proposed some pseudoscientific idea of cold nuclear synthesis. And people say that, oh, maybe it's also not so scientific, but you see that Raman scattering and surface enhanced Raman scattering become a very big branch of science. And you see that now his work, his pioneer work, has more than 5,000 citations. And when we say, when we place near the nanoparticle the fluorescence center, we have some resonance interaction, and it allows us to obtain from Raman scattering, allows obtain surface enhanced Raman scattering, and from fluorescence, some metal enhanced fluorescence. But to see these two effects together, not so much works are published about this. And therefore, we decided to check this possibility on the example of zinc phthalocyanine emitter. It's a molecule which is very popular now for organic solar cells and photodynamic therapy of cancer. And we placed this molecule on the surface of these gold islands, on these some exotic nanoparticles. And this work was done in collaboration with two scientific groups. One was a group of Dr. Elena Fesenka from the Institute of Physics, Ukrainian Academy of Science, and another group was from Austria. It was Institute of Applied Physics, and this group was led by Professor Thomas Clark. And what was registered, basically, as was achieved in Raman, we obtained several orders of enhancement for the signal, but when we saw the fluorescence, in fluorescence we obtained only like 1.3 times, something like this. And it was a question why it is so. And the question appeared not very easy, because not very much works were about the simultaneous analysis of Raman signals and fluorescence for the same samples, which prepares in the same rules and just in the same conditions. But we found very interesting work. It was quite old, like 1983, where this Raman scattering and fluorescence, which assisted by plasmons, is analyzed in the similar way. And here I just make a summary of the most important points of this paper. So they started from the very general ratio that intensity is a product of excitation efficiency, transfer efficiency, and emission yield. When we say about the transfer, it means that when we excite to some level and when we have emission from the same level, its transfer is unity. means that all energy is excited, it's go to the radiative channel, and therefore the transfer is 100% like unity. But when we have from the excited level, we have some non-radiative processes, which can be some dephasing or some thermal depopulation. And finally, when we have radiation from the level which is lower than excitation, then in this case we have transfer much less than unity. And coming to that cases which they and we analyzed, its first case is Raman scattering, and it's illustrated here by this energy diagram. When we excite to this excited level 1, it's relaxed without transfer. It means that from the same level it relaxes immediately. Therefore, this enhancement coefficient is defined by basically by the local fields. It's a local field of excitation and local field of emission, which is squared because intensity is proportional to electric strength squared, and then it's multiplied because we have two processes together, excitation and emission. And finally, these two coefficients in product, it gives like orders, like 3 orders of enhancement. But when situations changed, like we excited to one level and we have some, let's say, small dephasing, it means that emission starts from the level which is lower than excitation. In this case, it immediately gives like 2 orders decrease to this enhancement coefficient, because this non-radiative channels appears, and the energy which comes there, it basically did not allow us to obtain 100%. So these products of non-radiative factors is like 10 in minus 2, 10 in power minus 2. So the real enhancement coefficient which is left for fluorescence, it can be 1 order, like 10 times. And even this number cannot be used in general case completely, because it depends on the quantum yield of initial quantum yield of fluorophore. And this situation is depicted here. When we have excitation, when we have a lot of dephasing, thermalization processes, and then basically our emission starts from the level 0. Here it's excited level, but it's marked like 0 label, and this is ground state. So here we see that because of this, a lot of non-radiative channels, we have product of this 10 on the basically on emission yield. And when we have high quantum yield initially, this radiative rate is dominating, and for the surface rates here we have such numbers like the orders of these numbers, and finally it gives us 0.01. And therefore, when we make the product 10 multiplied by 0.01, you obtain not increase but even decrease in fluorescence. So basically, for the good fluorophores, which has quite high quantum yield, like 95%, it makes non-enhancement but decrease when we place this plasmon particle near. But when we have a fluorophore with non-radiative, where we have initially low quantum yield, it means that non-radiative rates are prevailed initially. It gives us such situation when this ratio of yields gives us ratio of rates gives us unity. And then we can, if we multiply this 10 factor to unity, it gives us 10. It means that in the best case, when our fluorophore is very bad, it means that it has very low quantum yield, we can obtain nice enhancement, like 10 times enhancement because of plasmons. And saying about this phthalocyanine, which we analyzed, it has quantum yield something like near 60–65%. So it means that it's not 95. It means that we have some room for enhancement, but still it's not very low to be enhanced hugely. Therefore, we obtained only like 1.5 times enhancement. And the same situation was when I have collaboration with another group in China, and we have tried to realize plasmon phosphor on inorganic basis. Like we used Mn4 plus ion, and we added some silver particles inside the system to see how they increase intensity. And we obtained also like very low, like 1.4 times. And it is maybe because we have already nice fluorescence, and we have not much room for increase because our quantum yield kind of like already not so bad. So in conclusion, Raman scattering occurs from the excited state almost at once after excitation. There are no time and way for non-radiative relaxation. So several orders enhancement coefficient in this case is defined mostly by local electric field enhancement coefficients. But in other cases, electrons can relax from excited to less energetic emitting states from which fluorescence occurs. And these relaxation channels decrease enhancement coefficient for fluorescence process comparing with Raman, and leave possibilities for only several times plasmonic enhancement in fluorescence if initial non-plasmonic fluorescence yield was low. Otherwise, there is no enhancement and metal surface quenched fluorescence. And finally, I would like to acknowledge our armed forces of Ukraine, territorial defense, and all volunteers and European Union states for support and heroic struggle and defense of Ukraine just now in this time. Thank you for your attention.
Thank you, Professor Dolgov, for very interesting talk and for the saving of time. We have quite a lot of time for discussion. We want to ask the speaker.
There is a question from the conference hall.
Kyiv National University. I have a question. How could you argue that your intensity, just theoretical question, is proportional to the multiplication of two transition probabilities up and down? I would say intensity is proportional to probability transition down from upper level to lower that you account for. At the same time, in turn, that transition can be proportional to the transition up, to the upper level, and intensity of the light, if you talk about fluorescence. So, and there should be also included such parameter as the decay parameter for single atom or molecule. Thank you. Is it a clear question?
Yes, I understood you. I just here maybe I clarify a little that when I say about this product, I mean that it's basically when we say about up transition, we mean the absorption cross-section and all processes connected with absorption, because the more you absorb, so the more you finally emit, and this I mean.
Yes, if you say something about environment where this transition happens, when you neglect a lot of effects. Thank you very much.
Other question, please.
One moment, we have one more question from conference hall.
Okay, please.
Thank you. My question is, how do you determine quantum yield of the emission in the presence of a plasmon field? do you take into account that absorption coefficient also increases when you increase the intensity of electric field?
Yes, it's a good question, because basically that paper on which I refer, they did not make it completely in one way, like theory complete and experiment complete. They make a kind of like situation when they make an equation, and at some point they say that, okay, we don't have this theoretical data, we can insert our experimental numbers into that equation which we have, and make a kind of like a judgment about the orders of effect. It's of course it's a very to say it more exactly and accurately, it's a big question to make it very accurately theoretically or very accurately experimentally, just take into account all effects, like distance between the emitter and the fluorophore, like kind of like interaction when you have several particles like interacting. You also have some effects on quantum yields, and so it's a kind of like indeed, and there are a lot of papers about these related things. But our desire was to understand what is the basically reason for such orders difference in enhancement, and they give us an answer. It's basically because of these non-radiative processes. It's just dephasing or some relaxation. It means that our thought initial was what will be more effective when we increase more this absorption and obtain higher coefficient, or we play with plasmons which will be coupled more with emission, not with absorption. But now I see that answer is that the more constructive way just to couple plasmon with emission, because when you have coupled with absorption, and if you have large Stokes shift between absorption and emission, this large Stokes shift already gives you a lot of way for these non-radiative processes, and these non-radiative processes will basically limit that plasmonic effect which we would like to see in emission.
Okay, thank you. Other questions?
No, we don't have in conference hall.
Okay, then I would like to ask speaker first concerning the absorption. Is it important that I think your plasmon frequency should be adjusted to the excitation frequency? Only then you can expect some enhancement of the absorption. Am I
yes,
right?
yes, and yes, you are right. And another point that like excitation and emission levels should not be very strongly separated. It works better for organic fluorophores, because for inorganic fluorophores you have a large Stokes shift, and this effect will be maybe if your plasmon will be coupled with excitation, with emission, it will be almost not coupled. Therefore, it's desirable to have coupled with excitation, and that emission not so far from excitation should be.
Okay, thank you. And other question simply is, it's a recent Nobel Prize for some stimulated fluorescence spectroscopy with high resolution. Is it possible to use some enhancement for such kind of spectroscopy? Because here it's you stimulate maybe only some changing of the dipole moments of the excitation, but in the stimulated fluorescence, it's important that you enhance field intensity.
I can say that that guy who collaborate with Elena and me, this Professor Thomas Clark, he is dealing with this super resolution in fluorescence quite much time.
Yeah,
And yes, and it's his business basically. Yes, it's possible. Basically, it's also for fluorescence spectroscopy. These super fluorescent things are possible.
Okay, so other questions? No questions. Thank you very much for the interesting talk. And what about Professor Przemysław Raczyński? He is not with us.
Oh, unfortunately, he haven't connected.
Okay. So next speaker, Professor Alexey Nazarov, with talk radio frequency plasma modification of molybdenum S2 2D material from Lashkarov Institute of Semiconductor Physics of National Academy of Science of Ukraine. Are you with us, Professor Nazarov?
Yes.